we will check the input type and reject the data, invalid data directly. So what we should do is just change a little byte of the input data and try pass the data through the system and make it accept, and then may crash the kernel or have some other effects. So let's take an example. Here's easy C structure, and we malloc data from memory and copy the data to message data. So what if we change the some bytes of the data, like the length? We change it from 23 to 1. Then we will malloc on a small memory, but after we exit the string copy, it will still copy the whole data to the memory, and this will overlap the memory and may crash the process. Okay, another example is how about to change the or remove the null bytes in the string, the null bytes. As we know in C language, when the string function is terminated by the null bytes, if we change it or remove it, like this one, it will copy the data through pass the previous null bytes and until to the next null bytes. This is also will overlap the memory, and also it may crash the process. What we have talked are two similar but different bugs. This with change every byte of the input data, we will try many attempts, and we will finally find these two bugs. This is the basic method of fuzz testing, and with this testing is very easy to write and use. And sometimes it finds some bugs, but we call it dumb fuzz or foolish fuzz, because in our modern systems, most time when we receive data or when we put data in the storage, there will have checksums. Whenever we change any bytes of the data, the checksums will get mismatched. Like this, in the highlight FF, after we change this byte, the new checksum will mismatch with the previous one. And if we put this data into the server, it will fail on the initial check and reject directly. This will limit the fault we can find. So with the this is why we call the previous fuzzing as dumb fuzzing, and with some modern fuzzers, it can whenever we change some bytes, it will update the checksums directly. And it will also update some others, like the inscription or encoding. And whenever we change anything, it will get a correct checksum, and then it will pass the checksum check and pass the data to the data consumer. Here are two famous commercial fuzzers. And the first one is the Konamikan defenses. It found the famous OpenSSL heartbeat bug. Another is pitch fuzz. These two fuzzers, after we config correctly, it will generate packages based on the RFC standards, and it will then fuzz or change some bytes of the message and update the checksums, and then send the malformed data to the server or receiver, and to see if there's any bad things happens. From now, we only test the, what we have talk about is test the receive side or the server side. But this is only half testing. Because we also want to test the client side. So how to test the client syz-callers? Here are two another examples. This is open source testing examples. One is Trinity and another is syz-kaller. Let's take some client syz-callers, for example. The common socket and then connection and send a message. And there are also some other syz-callers like get socket option or set socket options. So what comes into our mind first is how to test these syz-callers. I think the basic method is just to fuzz array parameters and input some random values with the correct type, like the socket syz-callers, we input random integers. But as we know, the valid domains only have 45, and the integer range is very large. So if we try array integers, this wastes a lot of times. So what we should do is to limit the input types, and we put more weight on the valid domains and less weight on the invalid domains. The same is as types and protocols or address. But how to make it more efficient? As we know, in the first parameter of connection is file descriptor. What we should if we do not have a valid file descriptor, then we can't go further. So what we should do is to wait the socket function to return the correct file descriptor and put it in the connection. Also, the same with the send function. So with the same with different domains like IPv4, IPv6, or netlinks, it also should have some with different actions. The different protocol types and like TCP, ODP, and SATP, it should also have different actions. This is what Trinity did, and it also find a lot of bugs, but there are still some downsides. As we know, it input the random values, but we do not know what code it has covered, and most time the Trinity only find the shadow bugs. Also, we do not know what it has been called, and so it's frequently no reproducer. With also the random input every time, so it's very hard to use it as a regression test. To improve this, then we have the code coverage guide fuzzing the syz-kaller. The theory of syz-kaller or the code coverage guide fuzzing is at the beginning we start an empty corpus program, and then we generate a new program or choose the existing program from the corpus and then mutate. After that, we run some programs and then interrupt it and then collect the coverage data from every syz-call independently. If a syz-call covered a code that was not covered before, we will minimize the program and put it in the corpus. Then we will go to the first step and run it again and again. Here is a method to collect the coverage info. First, we need to enable the kernel coverage option, and for example, in this if condition, we will insert 3 inline functions in before and in and after the if condition. And then after we run the fuzzers, it will know where we have been and what lines it has been covered. With this method, if we will know what has been run, and if there's anything happened, we will easily to create a reproducer and run it again. Here's an output of the syz-kaller. On the right side, it will show which lines it has been covered and which line hasn't. And on the left down side, it has the priority of each syz-calls. Here is the total bugs it has been found. It has already found more than 450 bugs in the past 2 years and more than 25 CVE bugs. This is very strong, very powerful and efficient. Okay, so here's the summarize. So it's how this we have known how the fuzzer testing develops from the dumb fuzzing to the smart fuzzing. With smart fuzzing, it will understand the data format and like some strings or integer, or it will also update the checksums, and also it will store some TCP sequence numbers and so on. It also could modify the data to gain better coverage, to increase the ability to detect certain types of issues. Also, it will have failure analyze and could generate reproducers. With some other plus options, the smart fuzzer, sometimes it has the ability to monitor the target if it has any fault, and also it may have result dashboard. Okay, some reference. Thank you. Any questions? Any questions? It has been found more than 450. Repeat your question. How many bugs is the syz-kaller has been found? In the picture, I just grabbed the result, and it has been found more than 450 bugs in 2 years, and also more than 25 CVE bugs. Yeah, and any other questions? Yes, please.
You said Trinity was bad for regression testing. Is syz-kaller better?
Yes, because you repeat your question. The Trinity is bad for regression testing, and the syz-kaller is better. The answer is yes, because Trinity input data is every time is most time is random, and it could not do every time if our code changed, and it can't realize, and so it's hard to find new bugs. But and also for regression testing, every time it's input the random data, so it's hard to cover the previous code. But syz-kaller, it has the data corpus, and every time it can run the previous fuzz programs and again. So it's better to use this tool. Any questions? Okay, thank you. Have a good evening. Yes, thank you.
Guys, it was the last speech of the day here, so there will be nothing more in this room. So if you are waiting for something, you are waiting in vain. No, nothing. And this room will be also locked in a few minutes.